Hey everybody, my name is Sarah Krieger. I am an emergency physician and intensivist at UCLA, and this is ICU EDU. Let's talk acid-base, but acid-base 2.0. So why do you care about becoming expert at acid-base? And the reason isn't to pass a test. The reason isn't because it's a really cool, sexy topic. The reason is because it really makes a difference in terms of your ability to understand what's going on with your patients and why. And there is information that you can get on your patients through ABGs that you simply can't get any other way. And if you don't know how to interpret ABGs in the clinical context of your patient, you are going to miss things. So let's take some examples. This was a 62-year-old female with history of obesity, hypertension, COPD, coming into the ED with altered mental status times 1 day. If we look at her ABG had a pH of 7.31, a CO2 of 81, O2 of 72, and a bicarb of 40. And the rest of her labs weren't that impressive. Her lactate was okay, her trope was negative, but she was super, super altered. And initially looking at these numbers, everybody really focused on that CO2 of 81. And so they were like, okay, this doesn't look so good. She's super, super altered. Her CO2 is high. And so she ended up getting intubated. And then I got called to admit the patient. And I was told that the admitting diagnosis was that this woman was having a COPD exacerbation with hypercarbic respiratory failure secondary to CO2 narcosis. The problem was that, after I came down and saw the patient, and she indeed was really profoundly altered, did a head CT, and it looked something like this. Huge bleed. Now, you could have actually figured out not necessarily that she had a huge bleed, but that the CO2 wasn't causing her altered mental status just by looking at that ABG. What about this gentleman? This gentleman was a 28-year-old guy, history of diabetes, heavy alcohol use, and he came in with profuse vomiting and abdominal pain. His ABG had a pH of 7.38, a CO2 of 37, an O2 of 85, and a bicarb of 23. The rest of his labs were notable for, one, his glucose wasn't all that high. It was in the 250s. His lactate was normal, and his lipase was 983. If you look at the rest of his electrolytes, his sodium 136, chloride 83, bicarb of 23. And the thing that people noted about these labs, this guy has diabetes, but his sugar's not that high. He's coming in with lots and lots and lots of vomiting and abdominal pain, and his lipase is in the 900s. So what happened with this guy? Well, this guy ended up getting aggressive fluid resuscitation. And he was admitted to medicine for an admitting diagnosis of acute alcoholic pancreatitis. And that actually wasn't the point that I got called on this guy. The point that I got called on this guy was the next morning when his ABG comes back. And somebody checked an ABG on him because I guess he wasn't breathing very well. He was getting really sort of short of breath, getting really tachypnic. And his ABG in the morning was a pH of 7.02, a CO2 of 12, an O2 of 88, and a bicarb of 5. Then, when the medicine person did labs, his glucose still wasn't that high. It was in the 260s, and his lactate was normal, but his beta-hydroxybutyrate was super elevated. Now, going back and looking at this guy's initial labs, you could have figured out that there was a decent chance that he might have been in DKA. And yes, he had pancreatitis, but that wasn't the only problem. And this is why we need to understand acid-base. Now, the problem is that this was how I was taught acid-base. 17 different steps, these incomprehensible diagrams. And the way that I was taught acid-base, I kind of was like, oh, it's some math, I need to learn it to pass the test and then call it a day, because it just wasn't bedside functional. And I think that when we're teaching and learning acid-base, we all have to keep in mind here that the goal is not to get a PhD in physiology. The goal is to construct a mental model that helps you understand what is actually happening with your patient. And really sort of knowing the detailed physical chemistry of acid-base is just not the point. The point is this mental model. Because at the end of the day, the most important thing here is, what story is the ABG telling you about your patient? I remember when I was a resident watching the first time that I ever watched one of Emil Motto's EKG lectures. And I had this moment when I realized, this guy is not looking at a bunch of squiggles and lines on a piece of paper. He's reading a whole story about this patient from looking at this EKG. And just like reading EKGs, when you're learning, it's hard. I mean, when you're learning to read, it's hard, right? Initially, you see a whole bunch of letters, then you need to start sounding out words. But then once you do learn to read, you read a sentence, you read a whole story. And EKGs and ultimately ABGs, it's the same thing. Once you know how to read them, truly read them like you would read a story, those numbers, it's not math. They are telling you a story about your patient. Now, before we learn how to read that story, we have to take a quick detour because the question a lot of you are asking your probably selves right now is, but what about VBGs? Because often, especially in the emergency department, we're not getting ABGs anymore. We are just getting VBGs. Why? ABGs are painful. They take a while. VBGs, we can just draw from the same place that we're drawing the rest of our blood. We don't have to poke our patient. And it turns out that there's increasing amounts of evidence that they give us the same information, that even in sick, critically ill patients, it's okay to just get a VBG and not an ABG. But wait. The problem with getting VBGs is that all of acid-base analysis, every method that we use to analyze what these numbers mean, is based on ABG numbers. So if I want to do this with VBGs, I have two options. Either I can reinvent all of acid-base analysis based on VBG numbers, or since I haven't done that yet and don't particularly feel like doing that, you could just do some extremely simple math to convert my VBG numbers into ABG numbers, then use all of acid-base analysis that's already been developed. So that's usually what I do. So let's say that I have a VBG and I want to convert it into the equivalent ABG numbers. Okay? It's actually super simple. What you do to convert your VBG numbers into ABG numbers is you add 0.05 to your pH and you subtract 5 from your CO2. That's about it. You don't need to do anything to your bicarb. The bicarb is going to be about the same or close enough that it doesn't matter. And the oxygen, I mean, your O2 doesn't tell you anything on a VBG anyways, so you can just ignore that. And really, to me, a lot of the only reason to get an ABG these days is if I need that oxygen. But a lot of the time we don't, and for acid-base analysis, we don't need it at all. So let's take an example. If we have a VBG, and our VBG has a pH of 7.35 and a CO2 of 45, and we want to convert those VBG numbers into ABG numbers, we simply say, okay, we are going to add 0.05 to our pH. So our pH of 7.35 becomes a pH of 7.40. And we are going to subtract 5 from our CO2. So our CO2 of 45 becomes a CO2 of 40. And then the rest of our ABG numbers, we don't need to do anything to. So now we've converted our VBG into an ABG, and we can move on and analyze it and figure out what it's telling us. So what story is our now ABG or VBG telling us about our patient? In order to really figure this out, I think that what we need to develop is a mental model for thinking about acid-base. And this, the way that I was taught acid-base, this right here is not a mental model. My acid-base mental model is really not about step 1, step 2 through step 17. It's about vectors. That is what I use to think about acid-base, and it looks something like this. You make yourself a vector map. And fortunately, these vectors only have 2 directions. This is actually much simpler than high school geometry. And there are 4 basic vectors on this map. So in the middle of the map is the pH of 7.40, where we would like to keep our patients. Then we have 4 different vectors that might be pulling this pH in 2 different directions, up or down. Our first vector is metabolic acidosis, where our bicarb goes down. Our second vector is a respiratory acidosis, where our CO2 goes up. Our third vector is a metabolic alkalosis, where our bicarb goes up. And our final vector is a respiratory alkalosis, where our CO2 goes down. That's it. That is my core mental model. Now, the basis, if you try and get a little bit more into the chemistry of acid-base, looks like this. You have your core acid-base equation, which is bicarb plus H plus gets converted by carbonic anhydrase into H2O plus CO2. The bicarb, that is the metabolic side of this equation. So our bicarb goes down, our pH goes down, our bicarb goes up, our pH goes up. Our CO2 is the respiratory side of this equation. And our CO2 goes up, our pH goes down. Our CO2 goes down, our pH goes up. Our metabolic side of this equation is handled by the kidneys, and that tends to be a slow process, whereas the respiratory side of this equation is handled by the lungs, which tends to be a fast process. And at the end of the day, the goal here, what this whole system is trying to do, is to keep the pH somewhere in the vicinity of 7.40. And the lungs and kidneys are trying to compensate for each other to try to keep that pH right about there. So that's the core chemistry of it. But our core mental model to think about this chemistry at the bedside is this. Acid-base status is an aggregate of multiple ongoing processes. That, to me, is the way to think about this. That is the way to approach our vector mental model. But how do we bring that to the bedside? Because we need a way to take our mental model and systematically use it at the bedside. And the way that I systematically apply my vector-based, acid-based mental model at the bedside is 3 things: state, process, story. And we are now going to spend the rest of this talk going through these things one by one and talking through how they work and how to apply them. So, state. State is talking about what is your pH. This one is a no-brainer. Is your pH normal versus acidemic versus alkalemic? Process. We have 2 different categories of processes: our respiratory processes and our metabolic processes. Our respiratory processes, how are we going to approach them? We are going to interpret the CO2 in the context of the bicarb. And our metabolic processes, we're going to interpret the bicarb in the context of the anion gap and strong ion difference. And finally, the story. This is the part where we figure out what these numbers actually mean in the clinical context of the patient in front of us. Okay, let's start with state. Is the pH normal versus acidemic versus alkalemic? And this is where I'm going to be the annoying attending when you say, oh, my patient is acidemic, and I'm like, no, but they have an acidosis. Or you say, oh, they have a lactic acidemia. No. Emia versus osis. I'm not annoying attending, but I try and only be really annoying when I think it matters. I don't know if I always succeed in that, but here we find ourselves. But let's talk for a moment about the difference between an acidemia and an acidosis, an alkalemia and an alkalosis. In general, in medicine, the emia versus osis designation, an emia is a state where you are at. And osis is a process how you got to that state. So in acid base, if we are in a state of acidemia, our pH is 7.15. The process by which we got to that state is an acidosis. If we're in a state of alkalemia, our pH is now 7.55. Our state is alkalemia. The process by which we got to that state is an alkalosis. Now, let's say that, for example, our pH is 7.25. That means that we're in a state of acidemia. You can only be in one state at a time, but there might be multiple processes that have led to that state. Similarly, we can be in a state of alkalemia with a pH of 7.45, and there might be more than one process that led to that state. Or even, we might have a pH of 7.40, be in a normal state. But if we have 2 vectors, 2 competing OCs, processes that are tugging us in 2 different directions, the net state can be normal, even though there are multiple underlying processes going on in the background. So at the end of the day, you can only be in one state at a time, but you can have multiple processes ongoing simultaneously. All right, now let's talk about those processes. So, as we said, acid-base is an aggregate status of multiple ongoing processes. And there are 4 variables that I think about when I think about defining any one of those processes. Is it an acidosis versus alkalosis? Is it metabolic versus respiratory? Is it a primary response versus a compensatory response? And is it acute versus chronic? Now, here's the thing. Unless you really want to get an A+ on the test, if that's not your goal here, all processes are not equally important. Now, because we were all taught acid-base in med school when the goal actually was to get an A+ on the test, we were all taught the processes as if they were equally important, but they're not. It's kind of like learning French or Spanish in high school. You know, they teach you every little detail that they can test you on, like where the accents go. But teaching you that doesn't actually help you go speak French when you go to France. It's just what they can test you on. So in acid-base, they teach you every single possible process, but at the bedside, they're just not equally important. And since the goal of this lecture is for you not to pass the test, I mean, if it helps you do that, great, but if that's what you really want to do, this is not the lecture for you. The goal is to build a mental model at the bedside. In that case, you can ignore a lot of the processes. You just can sort of ignore them. Because really, clinically, where the money is acidosis. So not accidentally, we are going to spend a lot more time focusing on processes related to acidosis. All right, we are going to start by talking about our respiratory category of processes. And this is where we're going to interpret the CO2 in the context of the bicarb. Now, why do we need to do that? Well, it's as if I was like, it's 70 degrees outside today. Okay, that is great, but that piece of information that it's 70 degrees outside is not that useful. I don't know what that means. I mean, are we in Alaska in January? Are we in, the middle of the Sahara Desert in July? Like, for me to know what it being 70 degrees outside today means, I need to know some context. And the same way, in order to interpret your CO2, you need to have the context of the bicarb to do it. So, first, what if the context of the bicarb is that the bicarb is low? We have a metabolic acidosis. We have a low bicarb. How do we interpret the CO2 in the context of a low bicarb? That is when we think about respiratory compensation for an acute metabolic acidosis. Because when you have a metabolic acidosis, what's your body supposed to do? It's supposed to compensate. And the degree to which it compensates should be proportionate to the degree of the acute metabolic acidosis. And you want to know, is my patient appropriately compensated for their acute metabolic acidosis? Now, there are a couple of math-involving ways that you can do this, but I strongly prefer not to do math at 2 a.m. unless I absolutely have to. So let's do this the non-math way. When you were thinking about, is your patient appropriately compensated from a respiratory standpoint for their acute metabolic acidosis? Here's the rule. When appropriately compensated, the CO2 should equal the last 2 digits of the pH. So let's say I have this ABG, pH of 7.24, CO2 of 24, O2 of 80, and a bicarb of 10. Well, our bicarb's 10, it's low, so we have a metabolic acidosis, but the patient is appropriately compensated because the CO2 is equal to the last 2 digits of the pH. So that's how you know, no math involved. Now, some people might desperately want to do Winter's formula and do extra math, and if you really want to, go bonkers. But they've actually looked at this and they basically give you the same numbers. Like there's no actual medical reason to do the math unless you really, really want to. So I usually go with this rule because I can just quickly glance at the ABG and know if my patient's appropriately compensated. And so what your patient should be doing on our vector diagram is if they have a metabolic acidosis, they should be having respiratory compensation to pull that pH back towards 7.40. Now, what if we have this ABG? We have a pH of 7.02, a CO2 of 40, an O2 of 80, and a bicarb of 10. Well, if you just first pass look at this ABG, you'll be like, oh, the CO2 is normal. It's 40. That's a normal CO2. Until you look at it in the context of the bicarb. Because our bicarb is only 10. We have a metabolic acidosis. So that CO2 of 40, which is quote unquote normal compared to, a normal value of CO2 of 40, it is higher than it should be. It should be significantly lower than that given the context of the metabolic acidosis. And so this CO2 of 40, that patient with this ABG actually has a respiratory acidosis on top of their metabolic acidosis. And so that's what their vector diagram looks like. They have a metabolic acidosis, but also a respiratory acidosis, even though their CO2 is 40, which is quote unquote normal, but not normal in the context of the CO2. Now, it's important to keep in mind that in acid-base, there is no such thing as overcompensating. Other walks of life, yes, acid-base, not so much. So, for example, if we start off with our ABG of 7.24 with a CO2 of 24, bicarb of 10, and then later we come back and we see the patient, and now that patient, their bicarb is still 10, but now their pH is 7.37 and their CO2 is 18. So their bicarb is still 10. Their bicarb is still low. So they should have a lower CO2 than a normal of 40, because they're compensating. But their CO2 is 18. It's lower than it should be. That's not overcompensating. Overcompensating doesn't exist. What that is, that CO2 of 18, that is a respiratory alkalosis. So this patient's vector diagram has a metabolic acidosis and a respiratory alkalosis. Maybe they're in pain. Maybe they're agitated. Maybe you didn't sedate them well enough. Maybe they have salicylate toxicity. You don't know, but that is a respiratory alkalosis because there's no such thing as overcompensating an acid base. All right, what about how do we interpret the CO2 in the context of a bicarb that is higher than normal, in the context of a metabolic alkalosis? So this is where we get into the potential clinical scenario of figuring out the baseline CO2 in a patient with a chronic respiratory acidosis, because this can be a very useful thing to do. And there's any number of reasons why a patient may have a metabolic alkalosis, but clinically, a lot of the time, when it matters, is when it's a patient with a baseline respiratory acidosis, and we need to figure out how are they compensated. Because the idea is this: if you have a chronic respiratory acidosis, your lungs aren't doing their job, and the kidneys are like, guys, okay, fine, if you're not going to do your job, that's cool. The CO2 is going to be high, so we'll just retain some bicarb to help you out and try and make our pH a little better. The kidneys compensate. And their compensation is proportionate. The higher the CO2 is chronically, the higher the bicarb will be chronically to compensate. And so here is the rule of proportionality. For every 4 the bicarb is above a normal bicarb of 24, the CO2 is 10 above a normal CO2 chronically. So let's say we have the following ABG. We have a pH of 7.30, a CO2 of 70, an O2 of 80, and a bicarb of 36. And we are trying to figure out, what does that CO2 mean? We have a CO2 of 70. It's higher than a normal CO2, obviously. But what does it mean? Well, we need to interpret it in the context of the bicarb. Is that the patient's chronic CO2? Do they live at a CO2 of 70? So let's do the math. And it's just a little bit of math this time. So with a bicarb of 36, we're going to say 36 minus 24. 24 is a normal bicarb. So 36 minus 24 is 12. Then we're going to say 12 divided by 4, because for every 4, the bicarb's above normal. So 12 divided by 4 is 3. Then we're going to say 3 times 10, because the CO2 is 10 above normal. 3 times 10 is 30. And then we're going to add that to a normal CO2 of 40. 30 plus 40 is 70. So in fact, that patient's baseline CO2 is 70. We can now look at this ABG and, interpreting the CO2 in the context of the bicarb, say, oh, they live at 70. Their CO2 is always 70. How do we know that? Because the bicarb is telling us that. So this patient right here with that ABG, her vector diagram looks like this. They have a chronic respiratory acidosis, pulling that pH down, but then they have a chronic compensatory metabolic alkalosis, pulling the pH back towards the middle. And the degree of that chronic compensatory metabolic alkalosis can help tell us about the degree of that chronic respiratory acidosis. But let's say we have this patient came in, and initially, let's say they came in a week ago and their CO2 was 70, and they came in for a broken ankle and their CO2 was 70. But they come in today and now they have the following ABG: a pH of 7.22, a CO2 of 90, an O2 of 80, and a bicarb of 36. Well, we can again do this math and calculate that with a bicarb of 36, their baseline CO2 is probably 70. But today, it's 90. So what does this patient have? Well, 90 is not their baseline bicarb. They have an acute on chronic respiratory acidosis. So their vector diagram has the chronic respiratory acidosis, the chronic compensatory metabolic alkalosis, but it also now has, in addition, an acute respiratory acidosis as well. So that is how we're going to interpret the CO2 in the context of the bicarb. Now let's talk about metabolic processes. So the metabolic category of processes are when we're going to interpret the bicarb in the context of the anion gap and strong ion difference. Now, the metabolic acid-base disorders are actually a lot more complicated than the respiratory acid-base disorders. So there's going to be an entire other lecture posted just on metabolic acid-base disorders, where we get into more detail about the anion gap, strong ion difference, and delta-delta. But for the moment, we're going to sort of talk through the basics so we can plug them into our model. The key thing to understand about metabolic acid-base disorders is this. You cannot interpret an ABG outside of electrolyte contents. Henderson-Hasselbalch is the way that most of us were taught ABGs, and it kind of ignores electrolytes in a lot of ways, but it turns out you really, really can't. And I am not for either the Henderson-Hasselbalch or Studer approach. I am for the what works at the bedside approach, and for me, thinking about both approaches is actually very helpful. So the way we're going to talk about this is not strict one or the other. It incorporates a little bit of both. Now, in the body is really wedded to this idea of electroneutrality. Within a given compartment, the number of cations, positively charged particles, always must equal the number of anions. Now, our major positively charged particle we're dealing with is sodium. Right? Now, there's also some potassium, calcium, magnesium floating around, but functionally for acid-base math, we usually kind of ignore them because the quantities are just so small, relatively speaking. So mainly we are just sort of focusing on the sodium. Then we have our anions, and our primary anions are our chloride and our bicarb, our negatively charged particles. But when you go back and historically you measured those, you notice that actually that meant that the anions didn't add up to the cations, and that is where we got this idea of the anion gap, this space where there's some extra anions floating around, and a normal anion gap is about 12. Okay, so now let's look at the metabolic acid-base disorders on our vector map. There are 3 types of metabolic acid-base disorders. 1, an anion gap metabolic acidosis. 2, a non-anion gap metabolic acidosis. And 3, a metabolic alkalosis. And let's go through each one. We are going to start by talking about anion gap metabolic acidosis because I think this is the one people are most comfortable with. So what is happening here is somebody is adding to your anion gap. In some manner, somehow, a bunch of unmeasured anions get added to your anion gap. Now, when that happens, when you add a whole bunch of added acid anions, what is going to happen? They're going to get buffered by bicarb in a 1-to-1 ratio. So 1 H plus anion, so 1 anion, plus 1 bicarb, 1-to-1 ratio. Now, what are those anions? Well, there's all kinds of different mnemonics for this. As some of you may know, I really hate mnemonics. I just like to think about things in basic categories unless there's a million, but it turns out there's not a million categories for what is going to go into your anion gap. And the most common things that you actually encounter clinically are lactic acidosis, ketoacidosis, renal failure where you get accumulation of phosphates, sulfates, and urates, and toxins. And your main toxins that you'll actually see are your toxic alcohols, aspirin, iron, and isoniazid. So that's it. Those are the 4 categories of anions that get added to your anion gap, lactate, ketones, renal failure, and toxins that cause an increased anion gap acidosis. Not that complicated. And I think this one we're fairly comfortable with. Now let's talk about the thing that people are not terribly comfortable with. Now let's talk about getting in to our non-anion gap metabolic acidosis and our metabolic alkalosis. And this is really when we need to go back to our electrolyte diagram and talk about things that are closer to the Stewart method. So, electroneutrality. We don't walk around with a net electrical charge. We just don't. The body's really, really into preserving electroneutrality, and in fact, it's so into preserving electroneutrality that the body will sacrifice pH to preserve electroneutrality. And I really think that was the key thing I had to understand to make the role of electrolytes in acid-base make sense to me. So in that context, we have 2 categories of ions. We're just going to look at our sodium, chloride, and bicarb. And our sodium and our chloride, those are our strong ions. And our bicarb, I like to call it our flex ions. So what is the difference between our strong ions and our flex ion? Strong ions are very, very stubborn. They are always ionized all the time. They don't care what anybody else is doing. They don't care what the rest of the body needs. They're like, I am just going to sit here and be ionized and whatever, you all can just solve your own problems. Flex ions, on the other hand, flex ions, ionization is situational. They're like, okay, I can accept a proton, I can give away a proton, I don't know, what do you guys need? What's going on? I can be flexible to the situation. Now, let's look at how the chemistry of this plays out a little bit more. So this is our core equation again of acid-base chemistry. Bicarb plus H plus gets catalyzed by carbonic anhydrase and converted into H2O and CO2. And that is a reversible reaction. And so your bicarb here can go from bicarb to carbonic acid by accepting a proton. And depending on the situation it finds itself in, it can make that switch. It is flexible. Whether it is ionized or not is situational. Now, what that means is that since the strong ions are stubborn and they're going to stay ionized, positively or negatively charged no matter what is going on, our flex ion, our bicarb, needs to flex into that space. So, for example, if our strong ion, our chloride, goes up, our bicarb flexes into that space by getting smaller. If it goes down, our bicarb flexes into that space by getting bigger. So let's take this example. We have a bunch of strong ions floating around. We have a bunch of chloride and a bunch of sodium. What happens if, let's say, I give somebody a bunch of normal saline and I add a bunch of chloride? Well, wait a minute. We now have too many negatively charged particles. So that's a problem because electroneutrality not preserved. Now, sodium and chloride, they're strong ions. They're just going to hang out ionized no matter what. So what are we going to do? Well, this is when our flex ion bicarb comes to the rescue. Because bicarb's like, okay, cool, I can just, produce some hydrogen, give you some positively charged particles, and fantastic. Okay, electroneutrality preserved. But look what we've just done to the pH. pH dropped, but electroneutrality preserved. Same situation in reverse. Let's say, okay, we have a lot of our strong ions, sodium and chloride, floating around. And instead, now we get rid of a bunch of chloride or, have now too much sodium, too many positively charged particles. Well, again, chloride and sodium not going to do anything. They're just going to stubbornly stay ionized no matter what. But our bicarb's like, okay, looks like we need some more negatively charged particles over here. And so now our bicarb helps out. It's like, I'm going to give away some of those. And now we have more negatively charged particles. But look what we've done to our pH. Our pH is now more alkalotic. So that is the idea, that our bicarb, our flex ion, is going to flex into this space between the sodium and the chloride, our strong ions, to maintain electroneutrality, but in doing so, that will have pH consequences. So, as you can now see, the difference between our strong ions, our sodium and our chloride, is actually very important in dictating our acid-base balance. And we have then given a name to that important difference, and we've uncreatively called it the strong ion difference, the difference between the sodium and chloride. And that difference is usually somewhere around 38. That's usually about where the strong ion difference hangs out. Now, it's important to note here that it's actually the relative amount of sodium and chloride that matters. It's not the absolute amount of chloride. It's not the absolute amount of sodium. It's the difference between the two, because that is the space that the bicarb needs to fill. So, given that, what is going to happen with our flex ion, with our bicarb, if the chloride goes up relative to the sodium? So instead of a strong ion difference of 38, our strong ion difference shrinks to 28. The bicarb also shrinks to fill that space. So a low SID, a small SID, less than 38, will give us a metabolic acidosis. What are the causes of this? A low SID metabolic acidosis, or a hyperchloremic metabolic acidosis, where our chloride is high relative to our sodium. There's a million of them, but the four that we really care about are: 1, normal saline administration, because when we give normal saline, we are giving a lot of chloride relative to the amount of sodium we're giving. Diarrhea is something that will also cause this. You see this a lot post-DKA, a hyperchloremic or low strong ion difference metabolic acidosis in the resolution phase of DKA, and you'll also see this in a renal tubular acidosis. Now, we'll get into the mechanisms of how these things occur in our lecture, the separate lecture focusing on metabolic acid-base disorders, but the key thing for right now is that a low strong ion difference, when it starts being less than about 38, can cause a metabolic acidosis, and the things that tend to cause that are normal saline, diarrhea, post-DKA, and renal tubular acidosis. What about when we have the reverse direction? Our chloride is now low relative to our sodium. Our strong ion difference is now larger. Okay, well, our bicarb is now going to expand to fill that space, and that will give us a high strong ion difference. So our strong ion difference is now maybe 48 instead of 38. And a high strong ion difference will give us a metabolic alkalosis. What are the causes of this? So, the four major important causes of a hypochloremic metabolic alkalosis are: 1, vomiting; 2, loop diuretics; 3, volume contraction; and 4, chronic compensation for a respiratory acidosis. And again, we'll talk about the mechanisms of these more in the other lecture, but for the moment, high strong ion difference greater than 38 tends to be caused by vomiting, loop diuretics, volume contraction, and respiratory acidosis compensation. So those are our three categories of metabolic acid-base disorders. We have an anion gap metabolic acidosis, a non-ion gap metabolic acidosis, and a metabolic alkalosis. Our anion gap metabolic acidosis, if that's all that's going on, your strong ion difference should be about normal. The things that are going to cause an anion gap metabolic acidosis, again, are lactic acidosis, ketoacidosis, renal failure, and toxins. In terms of our non-anion gap metabolic acidosis, in a non-anion gap metabolic acidosis, you're going to have a low strong ion difference, right? This is where you have a hyperchloremic non-anion gap metabolic acidosis. The main things that are going to cause those are normal saline administration, diarrhea, post-DKA, and renal tubular acidosis. And then finally, we have our metabolic alkalosis. That is when you're going to have a high strong ion difference of greater than 38, where your now chloride is low, a hypochloremic metabolic alkalosis. Chloride is low relative to sodium. The four things that are going to cause that in general are vomiting, loop diuretics, volume contraction, and compensation for a respiratory acidosis. Now, at this point, you may be wondering, okay, those are the three different kinds of metabolic processes we have going on. But if the bicarb is just the sort of vector sum of all of those metabolic processes, how do we know if we have multiple metabolic processes going on simultaneously? Because you can. And this is why the metabolic part of this, this step, the metabolic step doesn't just say, look if the bicarb is high or low. No. The metabolic step says even if the bicarb is normal, you still must interpret it in the context of the anion gap and strong ion difference. Why? Because it's like a tug of war, right? We can be like, oh, we have a lovely pH of 7.4. But if I have team metabolic alkalosis pulling really hard on one side, and team metabolic acidosis pulling equally hard on the other side, what it means is that our pH can actually end up looking quite normal. Our bicarb can end up looking quite normal, but that emia, they don't have any emias. They have a normal pH, but they do have alkaloses going on, and we can't miss them. So what is our clue? What is our clue to the presence of multiple metabolic processes? And our clue is there an anion gap? And this is the where there's smoke, there's fire principle. If there is an anion gap, there is an anion gap metabolic alkalosis. The number of conditions that will cause you to have an anion gap without an anion gap acidosis, there's a handful. They are so rare, just ignore them completely. For the purposes of everyday life, if there is an anion gap where there's smoke, there's fire, there is an anion gap acidosis. So, okay, there's an anion gap. So we know we have an anion gap metabolic acidosis. And so now we're going to ask ourselves the question, okay, check, we have an anion gap metabolic acidosis. Do we have one of the other metabolic acidosis or alkalosis? Do we have a second metabolic acid-base disorder? That is the question that delta delta asks. Delta delta asks, is the increase in anion gap proportionate to the decrease in bicarb? Now, we're not going to get into the detailed math of calculating delta delta right this second. We'll get into that in the other lecture. But today, we are going to get into the principle because the principle matters. And this is the principle. If you have an anion gap and you have an anion gap acidosis, but now let's say that we start adding things, right? We have an anion gap acidosis and we're going to add one anion. Let's just say we add a lactate. Okay, one lactate gets buffered by one bicarb at a ratio of 1:1. So our anion gap is going to go up by 1, our bicarb is going to go down by 1. And this always happens in a ratio of 1:1. So now if we add 4 lactates, then our anion gap is going to go up by 4 because we just added 4 lactates, and each one of those 4 is going to get buffered by 1 bicarb, so our bicarb should go down by 4. So if you have a situation of a pure anion gap metabolic acidosis, and that's all that's happening, the bicarb should go down by the same amount as the anion gap goes up. Okay. What if we have the following situation, however? What if we say, okay, we're again going to add 4 lactates. So our anion gap is going to go up by 4, but wait a minute, we see that, yeah, our anion gap went up by 4, but our bicarb only went down by 2. It should have gone down by 4, but it only actually went down by 2. What is going on? This is a tug of war, where we have an anion gap metabolic acidosis pulling our bicarb in one direction, but we have a simultaneous second disorder. We have a simultaneous metabolic alkalosis pulling our bicarb in the other direction. So when we have a situation where the bicarb decreases less than the anion gap increases, we have a tug of war, with a team metabolic alkalosis, a team metabolic acidosis, and the pH and bicarb ending up somewhere in the middle, because both teams are working really hard, but they're pulling in equal but opposite directions. Okay, alternatively, what about this situation? We again add 4 lactates, okay? We add 4 to our anion gap, so by adding 4 lactates, our anion gap goes up by 4. But we're like, wait a minute, our bicarb actually went down by 6. Our bicarb should only have gone down by 4. We only added 4 lactates, but it actually went down by more than we would have expected. That is this situation. That is when we have an anion gap metabolic acidosis, but we also have a non-anion gap metabolic acidosis. And in that situation, what you're going to see is the bicarb is going to decrease more than the anion gap increases. So that is how you're going to know if you have multiple acid-base disorders. And you actually have a lovely number that tells you about the net vector sum of your metabolic acid-base disorders. And I bring this up because we see this number on every single ABG we get, but there's a lot of confusion over what it means, and that is the base excess. So when I give lectures live and I sort of get to this part of the lecture and I'm like, who can tell me what the base excess is? I get a lot of different answers. Most of them are not right or even ballpark because I think we're just not taught this very well. But it's actually very simple. All the base excess is what is the vector sum of all ongoing metabolic processes? The base excess has nothing to do with any respiratory process at all. It basically says, okay, there's different metabolic processes, as we've talked about, that can pull you in different directions. There's an anion gap acidosis, a non-anion gap acidosis, and a alkalosis, all these metabolic processes. And it just basically says, okay, acidosis, you get a negative number. Alkalosis, you get a positive number. And then it just adds them up. And for every unit of acidosis, you subtract 1. For every unit of alkalosis, you add 1. And then that number adds to a negative or positive base excess. So if your base excess is negative 12, that means you have 12 units of metabolic acidosis. If your base excess is positive 12, that means you have 12 units of metabolic alkalosis. But if you have competing processes, it's going to be somewhere in the middle. Let's say you have 12 units of metabolic acidosis and 12 units of metabolic alkalosis. Your base excess is now going to be 0. So that is what the base excess is, a vector sum of all ongoing metabolic processes. And this is why the base excess is something we often use in surgical ICU, but less often in medical ICU. Because often in surgical ICU, the main question we're interested in is the person bleeding? And as long as the patient really only has a reason to have basically one bad thing going on, then it's kind of a useful number because, yeah, it lumps all the alkaloses and acidoses together, but unless I think my trauma patient also, for whatever reason, happens to have a coincidental and concomitant metabolic alkalosis, I can kind of say, okay, the base excess useful number because it tells me the processes. I suspect there's probably only one, and it's in the category of acidosis. That is the base excess, the vector sum of all ongoing metabolic processes. Finally, story. Okay, so this is the part where we actually get to why this is useful. What story are all of those numbers telling you about your patient? Now, the catch here is that just because you have these numbers, in the same way that a lot of what this lecture is about is been interpreting the numbers in context, you need to interpret the ABG as a whole in context, because the same numbers can tell a very different story depending on the lens you're looking at them through. So let's take an example. Let's take these numbers, and we're not even going to give the clinical context. And what we're going to do is just first analyze the numbers. So in this patient, yet to be undefined, we have an ABG with a pH of 7.18, a CO2 of 42, an O2 of 70, a bicarb of 15, and a base excess of negative 8. In that patient, we have an anion gap of 23 and a lactate of 4.5. So first, let's go back to state, process, story, and analyze this ABG systematically. And let's start with state. So what state is our patient in? What's the emia? Well, their pH is 7.18. They have an acidemia. Okay, that one was easy. They are in a state of acidemia. Now let's move on to process, and we are going to start with our respiratory process. And this is where we're going to interpret the CO2 in the context of the bicarb. So we're going to look at our bicarb, and our bicarb is 15. So we need to interpret the CO2 in the context of the bicarb, and we have a metabolic acidosis. So our CO2 should actually be low, and our CO2 is 42. And 42 does not equal the last two digits of our pH. The last two digits of our pH are 18. So we can just eyeball it and say, our CO2 is too high given the context of our bicarb, of our metabolic acidosis. So this patient has a metabolic acidosis, but they also have a respiratory acidosis. Okay, so we've completed the respiratory piece of the process. Now let's go on and interpret the metabolic piece of this process. And the metabolic step is where we interpret the bicarb in the context of the anion gap and strong ion difference. So our bicarb is low. We know we have a metabolic acidosis. Now let's look at our anion gap, which is 23. So we have a high anion gap, and our strong ion difference, which is 38. So we have a normal strong ion difference. So we have a normal strong ion difference, a high anion gap. We have an anion gap metabolic acidosis. Okay. Now we're going to go back and try and put this in context and figure out what this all means. Because I don't know what story this ABG is actually trying to tell me without some context. So we're going to go back to our ABG with an anion gap metabolic acidosis as well as a respiratory acidosis. And we're going to look and we're going to see our lactate's 4.5. Okay, so it seems like we have a lactic acidosis and a respiratory acidosis. Now, what if I told you that this was a 74-year-old female with a history of COPD presenting with fever, dysuria, and hypotension? Okay, in that patient, I see this lactic acidosis, and I'm like, okay, fever, dysuria, hypotension, this is not really terribly complicated. I'm guessing maybe this lady has septic shock from urosepsis. But why isn't she compensating from a respiratory standpoint? Well, probably because she has bad COPD, and her lungs will not allow her to appropriately compensate for her acute metabolic acidosis. So in this patient, this story that I'm being told by these numbers is acute septic shock with chronic respiratory acidosis due to chronic lung disease. Okay? What if we take the exact same numbers, pH of 7.18, CO2 of 42, bicarb of 15 with a lactate of 4.5, and instead the clinical context is now a 45-year-old gentleman presenting with a critical trauma with hemoperitoneum and a GCS of 111. Now, his lactic acidosis, he's probably in hemorrhagic shock, right? He just bled a liter of blood into his belly, and he's probably in hemorrhagic shock. That's explaining my lactic acidosis. But why isn't he compensating from a respiratory standpoint? Why is his CO2 42? Well, he just had a critical trauma. His GCS is 111. I am concerned that his CO2 is 42, not because there's anything wrong with his lungs, but because he has sustained significant neuroinjury and he's just not breathing well. He's hypoventilating inappropriately to his acidosis. So in this patient, the story these numbers are telling me are hemorrhagic shock and concern for possible significant neurotrauma. All right, same numbers. pH of 7.18, CO2 of 42, bicarb of 15 with a lactate of 4.5. But now our patient is a 20-year-old male with a history of severe asthma coming in with dyspnea and wheezing. Now what story are these numbers telling me? Well, that lactic acidosis, that is concerning to me because I'm worried that this guy maybe has status asthmaticus. And the diaphragm, it's a muscle, and it is working really, really hard. It is running a marathon, so that can contribute. In addition, this patient is intensely physiologically stressed, right? Running a marathon with your diaphragm's not easy. And on top of that, we've given him a bunch of other things to increase the lactate, like a bunch of albuterol, probably a bunch of epinephrine. So I think that the lactic acidosis is actually probably secondary to his severe asthma and status asthmaticus. And I'm getting really, really worried about this guy now because it sounds like he's sick enough in his static asthmaticus that we're getting a lactic acidosis from it. So that's explaining my lactic acidosis. And he's breathing, let's say at 40, and why can't he blow off that CO2 even though he's breathing at 40? because of his asthma, because of his obstructive lung disease, right? And so the story this is telling me is very, very profound respiratory failure due to status asthmaticus with hypercarbia from status asthmaticus. And then it's gotten to such a late stage of status asthmaticus that he now has a lactic acidosis. So as you can see, the same numbers can tell you very different stories depending on the clinical context. You can't look at them in isolation. So now if we rewind all the way back to the beginning, back to that first patient that we saw, our 62-year-old female with a history of obesity, hypertension, and COPD. Remember her? We started the lecture with her. She came in with altered mental status times 1 day. And she came in with a CO2 of 81 on her ABG. And remember, she was originally admitted for COPD exacerbation, intubated, and the altered mental status was attributed to the CO2 narcosis. But if we go back and analyze her ABG with our process, what's her state? pH of 7.31. She has a mild acidemia, okay? Respiratory. And this, for this patient, is the key part. We're going to look at our processes, respiratory first, and this is where we're going to interpret the CO2 in the context of the bicarb. And so her CO2 is 81, but that is in the bicarb context of, a high bicarb. Her bicarb's 40. So this is when we're going to say, okay, let's calculate her baseline CO2 because we suspect she does have a chronic respiratory acidosis. She has COPD. So we're going to use our rule for the bicarb's elevated above normal. The CO2 is elevated by 10 above normal chronically. And this lady's bicarb is 40. So we're going to do the math. 40 minus 24 is 16. 16 divided by 4 is 4. 4 times 10 is 40. 40 plus 40 is 80. And realize that her bicarb is telling us the story that she lives at a CO2 of 80. That is her baseline. She has a chronic respiratory acidosis and a chronic compensatory metabolic alkalosis. So when we look at these numbers and we interpret the CO2 in the context of the bicarb, we realize that actually her CO2 is always 80. That is baseline for her. That cannot be why she has altered mental status, because she lives at 80. Her altered mental status is acute. Her CO2 is not. Okay? But we can never stop halfway through, because now we're going to look at her metabolic processes. And this is where we interpret the bicarb in the context of the anion gap and strong ion difference. And what we see is that her anion gap is normal. It's 10. But her strong ion difference is quite high. It's 50. Why? So she has a strong ion difference, a hypochloremic metabolic alkalosis, where your sodium is high relative to your chloride. So we talked about how a high strong ion difference, when your strong ion difference is greater than 38, that'll give you a metabolic alkalosis. And we talked about the different causes of that. And one of the causes we talked about is chronic compensation for a respiratory acidosis, where basically your body chronically is like, well, the lungs aren't doing their job, so I'm just going to retain some bicarb and call it a day. So that actually makes a lot of sense when we now look at this, that her strong ion difference is 50, because if our hypothesis about her having a chronic respiratory acidosis and chronic compensatory metabolic alkalosis is correct, then that would actually make a lot of sense. So when we put this story together, we actually cannot say that this is a COPD exacerbation at all. We can't say that she's altered because of CO2 narcosis because she's at her baseline CO2. We need to go looking for another reason for her altered mental status. And in this case, the reason was that she had a head bleed. But now we can see that looking at those numbers initially, just glancing at them and applying our rules, we would have been like, yeah, that can't be it. It can't be a CO2 narcosis. That can't be why she's altered. What about our other patient we saw at the beginning? Our 28-year-old guy with a history of type 1 diabetes and healthy alcohol use. He came in with vomiting abdominal pain. His ABG was a pH of 7.38, CO2 of 37, O2 of 85, and a bicarb of 23. And then he had this really high lipase, a normal lactate, and a sort of, glucose in the 250s. He got admitted with acute alcoholic pancreatitis, and then after getting a bunch of IV fluid, the next morning, his bicarb was now 5, his beta-hydroxybutyrate was 1,000,000, and it turned out he was in DKA all along. So let's look at this guy. Let's take his numbers and state. Actually, his state is fine. His pH is 7.38. But this is why you have to be systematic and go through your process every time with every ABG, because just because the pH is normal doesn't mean there's nothing going on. So, pH, his state is normal. But state is different than process. Processes, and there might be underlying processes going on that just add up to a normal state. So first we're going to look at our respiratory processes. We're going to interpret the CO2 in the context of the bicarb. And this guy's bicarb is 23. It's basically normal, right? And so with a normal bicarb, your CO2 doesn't need to do anything in either direction. Okay, so his CO2 is 37, so that seems reasonable. We don't seem to have an acute respiratory issue going on here. But now we get to what turns out to be the important part with this patient. We are now going to interpret the bicarb in the context of the anion gap and strong ion difference. His anion gap is 30, right? His anion gap is 30. His bicarb is 23, it's normal. His pH is 7.38, it's normal, but his anion gap is 30. And remember, where there is smoke, there is fire. If there is an anion gap, there is an anion gap metabolic acidosis. And this is where we get in to our delta-delta, that we're like, wait a minute. We need to ask ourselves, wait a minute, there was an increase in anion gap, but the bicarb didn't really decrease. Because if we look at this, we're like, our anion gap is increased, it's 30. But the bicarb really didn't decrease almost at all. The bicarb's normal. It should have gone down a lot more than it did. What must be happening? Well, if we have an anion gap metabolic acidosis, our anion went up, but our bicarb didn't go down, there must be a second ongoing process. There must be a metabolic alkalosis that is pulling that bicarb closer to the middle. This is tug of war, where we have team metabolic acidosis, anion gap metabolic acidosis, in this case, pulling in one direction. We have team metabolic alkalosis pulling in the other direction, and they are both pulling in equal but opposite directions. So our bicarb and our pH are actually just fine. They're normal, even though these two teams are actually working quite hard. So why? Because we've identified that we have an anion gap metabolic acidosis, but where is this metabolic alkalosis coming from? Well, let's take a minute and let's look now at our strong ion difference. So, our strong ion difference in this patient is 53. Let's talk about what that means. A strong ion difference of 53 means that your chloride is low relative to your sodium. And so that strong ion difference of 53, that high strong ion difference means that you basically have a hypochloremic metabolic alkalosis. What are the causes of that we talked about? Well, there were 4 of them, but in this particular case, vomiting. This kid has been massively vomiting. Probably initially he did have pancreatitis, vomiting like crazy, and that's probably what pushed him over into the DKA. He's probably acute pancreatitis followed by DKA, presumably, but he's vomiting so much that he has given himself a hypochloremic metabolic alkalosis that is competing with his metabolic acidosis, with his anion gap metabolic acidosis. So how do we put this whole story together? Well, yeah, acute pancreatitis with an anion gap acidosis. And for the same reason that he has that high strong ion difference, he probably has a low glucose, because as you can get in a number of situations, if you're vomiting like crazy, you can sort of have a euglycemic DKA. So it's probably related that his glucose is, actually not that bad, and he has such a profound hypochloremic metabolic alkalosis. So that is how I would put together this initial story, that we have team metabolic acidosis, team metabolic alkalosis, both pulling in equal and opposite directions. So his admitting diagnosis of acute alcoholic pancreatitis was correct, but looking back on those numbers, he also probably had DKA at the time, because we know he had that acute metabolic acidosis. His lactate was normal. He has a history of diabetes, and the vomiting would probably explain why his glucose wasn't that high. That's what I think is going on. So then what happened? Overnight, he got admitted. He got a bunch of fluid, probably normal saline, so we just gave him a bunch of chloride. We also fixed his contraction alkalosis. And what has happened? We didn't give him DKA, but we didn't do anything to fix it either. We didn't give him any insulin. So what happened? Well, initially when he showed up, we had team metabolic alkalosis, and they were a pretty solid team, right? They probably had a hypochloremic metabolic alkalosis from vomiting. They also probably had a contribution of a contraction alkalosis. But then we gave him a bunch of IV fluids, and they left the field, leaving team metabolic acidosis by itself, and voila. So that is how we think about those two patients. And that is acid-base 2.0. We think about acid-base status as the aggregate of multiple ongoing processes. We map that mentally on a vector diagram, and then we go on to apply our mental map systematically at the bedside through state, process, story. State is our pH normal versus acidemic versus alkalemic. Process, which processes are contributing to that state. Our respiratory processes, where we interpret the CO2 in the context of the bicarb. Our metabolic processes, where we interpret the bicarb in the context of the anion gap and strong ion difference. And finally, and most importantly, what story is that APG telling you in the clinical context of the patient in front of you? Thanks for listening.